Have you ever looked at a radical function that's all stretched and shifted and just frozen? You're definitely not alone. But here's the secret. Every single one of those complicated-looking graphs is just a really simple one wearing a disguise. Today, we are going to crack the code on these functions, and we'll do it step by step.
So, here's the game plan. We're going to start with the two parent functions. They're our foundation. Then we'll learn all the moves, how to slide them, stretch them, and even flip them upside down. By the time we're done, we'll put it all together and you'll see how this whole visual approach makes finding the domain and range, well, almost ridiculously easy.
Okay, first things first. Before we can start transforming anything, we have to know our starting point, right? So let's meet the two parent functions. Think of these as the original blueprints for every single radical graph we're going to look at. So what even is a parent function? It's exactly what it sounds like. It's the simplest, most basic, kind of stripped-down version of a function in its family. Every other graph we make from here on out is just a modification, a transformation of this original blueprint.
Meet the parents. On the left, we have the square root function. You see how it starts right at the origin at 0, 0, and then just curves up into the right? It only exists for positive x values. And on the right, that's the cube root function. It's got this really cool S-curve shape, and it goes on forever in both directions. These two shapes, that's it. That's our foundation. All right, now that we know our parent functions, let's start messing with them a little. We're going to start with the easiest moves in the book, just sliding the entire graph up, down, left, and right, without changing its shape at all. Okay, don't let this equation scare you. I know it looks a little intense, but this is basically our master key. Each one of these letters, A, B, H, and K, is just a simple instruction. It tells us exactly how to move or change our parent graph. So let's decode it, one piece at a time.
We're going to start with H and K. These are the easiest ones. You can think of them as the location parameters. Their only job is to pick up the graph and slide it somewhere else. They tell us where our new starting point is going to be.
The K parameter is probably the most straightforward of all of them. It's our vertical shift. If you see a +4 like this, the graph moves up 4 units. If it was a -4, it would move down 4 units. It does exactly what you'd expect it to do. Pretty simple, right? Now, let's talk about H, the horizontal shift. This one's a little bit of a trickster because it's kind of counterintuitive. So take a look at this function. Your gut instinct might tell you one thing, but what do you think? Does that x minus 3 move the graph to the left or to the right?
And surprise! It actually shifts to the right. Here's the catch, and this is super important. The formula is x minus h. The shift is whatever h is. So when you see x minus 3, h is a positive 3, which means we move 3 units to the right. If you saw x plus 3, you'd have to think of that as x minus -3, so h would be -3, and you'd shift left. It's always the opposite of the sign you see.
Okay, we've totally got sliding down. Now for the really fun stuff, actually changing the shape of the graph. We're going to start with the A parameter. This one controls all the vertical action, making the graph taller, shorter, or even flipping it upside down.
So how does A work? Well, it multiplies every single y value on the graph. So if A is a number bigger than 1, like 2 or 5, it's going to stretch the graph vertically, making it look taller. If A is a fraction between 0 and 1, like 1/2, it squishes it down vertically. And the really cool part? If A is negative, it flips the entire graph over the x-axis. Now, reflections can be a bit confusing, but it's all about where you put that negative sign. If the negative is outside the function, it's affecting the output, the y value. So that's a vertical flip over the x-axis. But if the negative is inside with the x, it's affecting the input. So that's a horizontal flip over the y-axis. Inside or outside, that's the key.
All right, pop quiz time. Let's say you and a friend are looking at this function. Your friend says that the negative sign means it's a reflection over the x-axis, but you think it's a reflection over the y-axis. Who's got it right?
You do. You're totally right. The absolute key here is noticing that the negative sign is inside the function, attached directly to the x. That means it's a horizontal change, which is a reflection across the y-axis.
Okay, is time. Time to tackle the last parameter, and let's be honest, it's usually the trickiest one for people. This is the B parameter. If A was in charge of all the vertical stuff, B is its horizontal counterpart. It handles horizontal stretches, shrinks, and reflections.
And here's where things get weird again. Just like H,
The b parameter is totally counterintuitive. A b value of, say, 4 doesn't stretch the graph horizontally. It actually shrinks it. It squishes it in from the sides. And a fractional b, like 1/3, does the opposite. It stretches it out. It's all about the reciprocal. And of course, a negative b gives us that same horizontal reflection over the y-axis we just saw.
All right, deep breath. We've met our entire cast of characters, A, B, H, and K. Now it's time for the main event. Let's put them all together and walk through a full transformation, from the parent function all the way to the final graph. Now, to keep things from getting chaotic, it really helps to follow a specific order. My advice? First, find your new starting point. Just grab boop. Then, deal with any horizontal changes from B. After that, apply the vertical changes from A. Once you know where you're starting and which way the graph is oriented, you're ready to sketch the final curve.
Let's see this in action. We start with our parent, the good old square root of x. Now that +3 inside means our h is -3, so we shift left 3 spots. Then that -2 out front is our a. The negative flips us over the x-axis, and the 2 stretches us vertically. Finally, the +4 at the end is our k, and it shifts everything up 4 units. See how all those little instructions build on each other to give us our final graph?
And now we get to the big payoff. All this visual work we've been doing with graphs actually makes finding the domain and range, which can feel really abstract, incredibly simple and, well, visual.
This table really breaks it all down. The domain is just all the possible x values, right? So it makes sense that it's only affected by horizontal changes, our h and b. And the range, well, that's all the y values. So it's only affected by the vertical changes, our k and a. It's that simple. Horizontal stuff affects the domain, vertical stuff affects the range.
So let's apply that to our big example. For the domain, we just have to follow the one big rule for square roots. The stuff inside can't be negative. So x plus 3 has to be greater than or equal to 0. A little algebra, and we get x has to be greater than or equal to -3. For the range, we know our starting y value is our k, which is 4. And since our a was negative, we know the graph opens downward from there. So our range is all y values less than or equal to 4. That's it. No guesswork needed.
So what's the big takeaway here? It's this. You never, ever have to graph a complex radical function from scratch. Every single one is just a simple parent function that's been moved, stretched, or flipped. The equation gives you a clear set of instructions. And once you learn to read that code to see what A, B, H, and K are telling you to do, you can graph anything.